Hey guys, welcome to your second chapter 11 video. Let's see, we were talking about randomness, we were talking about the importance of randomness. Randomness is at the heart of everything we're doing in simulations in chapter 11. It is the crux of our discussion in observational studies and experimentation, along with sampling in chapters 12 and 13. And 11, 12, and 13 will be the next unit. Once we finish that third chapter, we're going to take another test. So you should have a third unit exam by the time you hit Christmas break. So where we had left off, we were in the notes. We were using a simulation to come up with an estimate for how many shots this free throw shooter might be able to make in a row without missing if she is 80% accurate from the free throw line. Okay, and we're going to look at another example that should be a good refresher as to how this worked. Remember that the calculator function that we were using a lot was randint, which is available from the math probability menu. I'm not going to go back to that. You can watch the first chapter 11 video if you want to see discussion on that. So, again, I'm not going to reintroduce the terminology. I want to get in and get out with this video. If instead of the basketball player's success rate being an 80%, it was 72%, how could we change our simulation to reflect this different free throw success rate? Well, a component is still just fundamentally that most basic random event. So a component would be, in this case, a simulated free throw shot. Okay, the outcomes obviously are a hit or a miss. We want to connect random numbers to the components. Well, okay, so if this player is 72% accurate, there are multiple ways that you can use randint to generate numbers to determine whether or not she is hitting or missing a shot. You could, for instance, 72% of 100% of all the events that could occur, you could reduce as a fraction to be 18 over 25, so you could say, okay, on my calculator I'm going to produce random integers between 1 and 25, where anything between 1 and 18 is a hit, because 1 to 18 is still 72% of all the available numbers from 1 to 25, or you could keep it simple and use randint of 100, from 1 to 100 rather, and produce random integers between 1 and 100, where 1 to 72 would be a hit. So there are multiple ways that you can connect your random numbers to the component that you've specified above. There's no correct answer there. There is, however, there are, however, shortcuts. Think it through before you choose the random integers. For the sake of making it easy in this case, we're going to allow randint from 1 to 100 to represent each shot. Okay, we're also going to specify, we're going to define how we choose our hits and our misses. Results from 1 to 72 represent a hit, all else a miss. Okay? So we've got our connection between the random integer function we're going to use and the component. Now, I can't remember if I said this last time or not. It is okay in this problem to use randint 1 to 100 because on the AP exam, you will not be allowed to use randint 1 to 100 or 1 to anything. You won't use the randint function at all. They are going to give you a random number table, which is available on the October 24th calendar event on My Big Campus. You need to, well, really you need to print that off. Unless you have access to that on your netbook here at school. Some people's netbooks are not so hot. But you need to have access to that random integer table, that random number table rather, going forward in this unit. Randint, however, is more convenient, so I want to show that as well. And there's no harm done in showing a couple of methods to do the same thing. All right, that's the first thing I wanted to say. Second thing I want to do, I'll do after actually I get through number 5. Okay, so we want to define a trial. A trial is a collection of components, okay? A trial in this case is the random generation of two-digit numbers, let's see, until we see you can either say a random integer between 73 and 100 or a miss, because we've defined already what a miss is. So either way is okay. All right, define the response variable. We are keeping track of the number of shots she makes consecutively. We are going to accumulate our trials or aggregate them, add up all the responses to all our trials, and then that will determine our best guess as to the likelihood that she will hit X number of shots consecutively, where X is that aggregated response. Okay, so the random variable here is equal to, we can define that as, I'll stick with the capital Y like I had done in the first video, where that equals the number of two-digit numbers generated minus 1. Again, because we're not caring to keep track of the miss, which stops the trial. Okay, now I'm going to pause there before we go to the table, which will help with our simulation, and read to you what a problem that you're going to encounter in this book would be like, where you would use a simulation. Notice, this problem does not do a lot of things. Listen, a person with type O positive blood can receive blood from only from other type O donors. About 44% of the U.S. population has type O blood. At a blood drive, how many potential donors do you expect to examine in order to get 3 units of type O blood? It's not asking what a component is. It's not asking what the outcomes of the components are. It's not asking about a connection between your random number generation and a component. It's not asking about trial, response variable, any of that. You need to be able to identify that these things need to be discussed before you run a simulation. Okay? Here again, you're going to see this on the AP exam. They are not going to spell it out for you as to your solution method. That's part of stats. The math in stats I don't think gets tough. But, and you guys have already hit this, identifying what something means, either from a description or a question, or trying to explain what the math that you're using means, that's where stats gets tough. Okay, so you need to be able to go through this process of component identification, outcome, specification, connection between the random numbers, etc., on your own every time. Okay, I'm not going to ask you on the exam to do these things. That needs to be done. You will miss points if you're not doing that. All right, let's run our trials. Let's analyze the response variable, and then we'll state our conclusion in context. So we've got this table. Here again, I think I said last time, refer to the Chapter 11 Part 1 video. I want to say I suggested 20 trials per simulation. I may have said 30, but I think I said 20. Okay, so again, I'm not going to run through all the rand-int repeats because that's just tedious. So we've got trial number. For the first column name, we've got the outcomes. And you've got Y, which is the response variable we're keeping track of for each trial. So we're going to go down to 1, 2, 3, 4, 5, 6, and I'll use 7 again. First trial, I got a 91. So she had 0 consecutive hits. Okay, then I saw a 63, a 44, and a 96. So she had 2 consecutive hits. Then I saw a 52, 67, 41, a 9, 7, and an 83. So she had 5. I found then a 5, 48, 7, and 88 for her next shots, leaving her with 3 consecutive hits. I saw for the 5th trial a 31, a 34, 50, 43, and 96. Leaving her with another 5 consecutive hits. I saw a 56 and a 93, which is 1 consecutive hit, and then a 71, 14, 57, and finally a 73, leaving her with 3 consecutive hits. Okay? All right, so we've kept track of a response variable for each new trial. They want us to analyze the response variable and state a conclusion in context. So that involves the following. from the results of our simulation, we see that what is that? There we go. Okay. We see that the shooter could expect to see y1, the first outcome of our trial, plus y2, plus onwards and onwards up to y6, the second to last trial, plus y7, divided through by 7, which is equal to 2.714, or approximately 3 shots hit. Hit in a row. Okay. And again, it's been 2 weeks since I've made the Chapter 11 Part 1 video, so I can't remember if I told you guys this or not last time. Frequently, when you're analyzing your response variable, as long as you guys have defined your response variable well, the analysis just involves tallying all the response variable outcomes. That is to say, add these up, divide through by the number of trials, and that will generally give you the thing that you care about. Now, there are exceptions to the rule. Don't go into the Unit 3 test saying that, or thinking that that's all you have to do to analyze a response. It depends upon the context. All right. Okay. So we've done our analysis. Easy peasy. Not much to that. So we want to look next at how would a trial in our response variable change if we wanted to know how many shots she might make out of 5 shots she takes. Still, in the original context, we were looking at an 80% success rate. We're going to look at that here too. So, component is not changing. That's the most basic fundamental event. That is a simulated free throw shot with a trial being a random number. This is changing. A random generation of numbers. Wait a second. Oh, that's right. Okay. When I was setting these up, let me actually see if I even want to include that example. Let me go ahead forward here. Okay. No, that first example is the one that I want. Okay. My mistake. So, simulated free throw shot. Trial is the random generation of 5 shots in the interval from 1 to 100. I'm using the brackets to denote that we're including 1 and 100. The response variable here, we'll let y, sticking with that notation, equal the number of digits between 1 and 10. Okay? Why would I write that? Okay, I don't think the response variable is correct. We want to keep track of how many shots she might make out of the 5 shots she takes. We did not connect. Okay, in this case, I really should have included space for connecting the random number generation to the component. So let's continue to use randint from 1 to 100, like we had said we were going to do in the trial. And the response variable here will be the number of digits between, between 1 and 80. Okay, because those are all of my hits. All right, so every trial is going to stop after the 5th generation of random numbers, and then we'll have the number of shots she's made out of 5 for each trial, for each row of the table that we're about to get to. And we'll tally those, divide through by the number of trials we ran, and that'll give us the likelihood of her making 5 shots consecutively. Okay, so there's my explanation for the last piece, the last question, how we would determine how many shots she might make. All right, so that was just the setup. How would a trial and a response variable change if we wanted to know her chances of hitting, both shots when she goes to the line to shoot 2? All right, so the component has not changed. It's still just the simulation of a free throw shot. A trial is going to look like the random generation of two-digit numbers. Okay, notice with all these trial definitions here, we're specifying when we stop generating the numbers. We're not just saying that we're generating them. You need to spell it out. Think about if you were writing explicit instructions for a cookbook. You're going to say, okay, you do this first, then once this happens to the batter, to something in the pan, whatever, then you do this next thing. You stop doing what you've done there. Okay, think of this as a recipe for how you're going to develop your simulation. Response variable here. Why am I doing this? I just said we were not going to do this. Response variable would be let y equal a 1 if she hits both 0 otherwise. That's how I would do this. Now there are other ways to do this. And so basically, let's say when you're running your trials, you had, for trial number 1, you had a 1. She hit both shots. For trial 2, she got a 0. For trial 3, she got a 0. So for the second and third trial, she did not hit both shots. Okay, so you could analyze this response variable by saying, okay, your trial 1 response, y1 plus y2 plus y3 divided through by the number of trials would be 1 plus 0 divided by 3, which is a 33% probability of hitting both shots. Okay, so we went ahead and did that one anyway. All right, on the AP exam, is this the last example? It sure is. Cool. On the AP exam, you'll be expected to use a random number table to develop simulations. Let's use one now for a simulation. Suppose we are randomly selecting 3 students from the class to speak at a parents' night about the joys of taking AP Stats. How likely is it 3 girls will be present for the parents' night? We'll use our own class's student population. Well, when this was developed, the class was it was convenient. We had 25, was it? Let's see. No, there were 20 students in the class, and okay, so the class population was 20 students in all. There were 11 boys, 9 girls. Okay? All right, so how can we identify a component? Well, that is going to be just the simulated selection of a student from the class. Okay? So it's, again, just the most fundamental random event that's occurring in our simulation. Specify the outcomes of the components. That's a boy or a girl. The random numbers connected to the components. Well, here, let me pull up the random number table. The idea is this. Can I move that around? Yeah. Okay. The idea is this. You've got all these digits that you can choose from. And the best method, because these digits were generated randomly, and you've got a lot of them to keep track of, start upper left, go from left to right. In this case, we may be able to get away with, for each new row, that can be a single trial. So that'll be the random selection of 3 students. And then the next row of random digits we can use as a separate trial. Okay, so we'll use 7 rows in this case, where we're choosing the digits to represent the kids. Now, obviously, because if you look at the breakdown of the class, 11 boys, 9 girls, I obviously don't have few enough outcomes, or few enough kids to choose from, rather, students to choose from, that we can just use digits between 0 and 9. It doesn't work that way. We've got 20 different students to choose from. So we're going to have to use more than one digit. We can use 2 digits in this case, where the lowest possibility could be 2 consecutive zeros. I'm trying to scan to see if I can find any, but oh, nope, there we go. 2 consecutive zeros right here would be the lowest possibility, with 2 consecutive 9s, like right over here, being the highest possibility. Well, 0 to 99 is 100 possible different random numbers generated in all. So what we can do is recognize that 11 boys of the 20 students in all is 55% of all the kids in the class. So we're going to use a random number table such that where we're choosing 2 digits from 0 to 99, 55 of those outcomes, 55% of them, in this case 55 exactly, of those outcomes will represent the boys. Okay, and the remaining 45, 9 out of 20, 45%, wrong button, 45% of those outcomes, the remaining 45 digits, will represent the girls. So let's connect the random numbers to the components. We got to be careful that, and we'll get to this with the trial. With the random numbers, if we only have 20 kids in all. So let me see how I wrote this in the notes. We're going to let 2-digit numbers represent the students in class where 0, 0 to 0, 4 is a boy. Okay? Because obviously I can't just assign a single 2-digit number to one kid, because in this case we've got way more digits than we have students in the class. So we need to use some, I don't want to say duplicate, but we do want to assign multiples to individual students. So 0 to 0, 4 is a boy or a young man. We've got 0, 5 through 0, 9 is a boy. Okay. Notice the way that I'm getting the number of digits I'm assigning to each of these students. Your 20 divide into the 100 digits we've got to use in all. That leaves you with 5. So every one of these students needs 5 of the 100 digits we have available. Okay, so 0, 5 through 0, 9 is a boy, all the way up to 50 to 54 is a boy, and then let's see if we can get this in. 55 to 59 is a girl, on up to 95 through 99 is a girl. Okay, so a little bit more complicated when you're using the random number table. You can't keep it as simple as, oh, hey, we've got 20 kids, we'll use 20 random numbers, end of story. All right, so a trial is the selection of 3 students where a student cannot be repeated. Okay, so you can't see the result 0, 0 also selected with 0, 2. That would be the same guy selected 2 times. That's not going to happen because we're choosing 3 separate students from the class population. So the response variable here, we'll let y equal the number of 2-digit numbers greater than or equal to 55. Okay, anything higher than 54 will be the girls, and we want to know approximately how many will be girls in this selection. Is that right? How? Oh no, that's not right. the question was, how likely is it 3 girls will be present for the parents' night? Well, so there are only 2 outcomes we really care about. For each trial, we want to know, were there 3 girls or weren't there 3 girls? So it's not the number of 2-digit numbers greater than or equal to 55. It is, wow, that's odd that it's coming up so late. We want to keep the current color scheme. Okay. Y is going to be a 1 representing, hey, it happened. 1 if 3 2-digit numbers greater than or equal to 55, 0 for all else. Okay, so it's a success if you had 3 girls selected, it's a failure otherwise. All right, so using the random number table, we've got, again, our trial number over here. We've got the outcomes in the middle column. You've got the response variable y that we're keeping tabs on. Did I use 7 trials here? I sure did. Got 1, 2, 3, 4, 5, 6, and 7. So the outcomes. Let's see if I was correct in remembering that I used 1 row for each trial. Okay, so we see first an 80, followed by a 94. Those are separate children. And then you've got a 25. Okay, so all are separate students. We'll write those down for the outcomes. 80, 94, 25. So the outcome would be a 0. That was a failure in this case. All right. Then we can just go ahead and use the next row for the next trial because we're not choosing that many numbers. You could alternatively, if you suspected that a trial would use a lot of these digits, you may not want to go ahead and start in another row. Okay? And that's actually something, apologize for not doing this. Looking back here in the setup, in the trial definition right here, so that the AP grader can understand how you chose your digits, you need to say not only, in this case, we would say that 55 to 59 is a girl, 95 to 99 is a girl, etc., all that. We also need to specify, for each new trial, we're selecting random digits from a new row of the random number table so that they can break down what you're doing. All right, so I saw next, again, for each new trial number, we've got a new row. So 35, 63, 21, another no. 13, 30, 63, all unique students, another no. I saw a 35, 65, 00, no. I saw a 78, 50, and a 99, which was a no. I saw a 44, a 90. Now I've got something scrawled out here. Let me see in the 6th row. And then a 54. Okay, so again, 3 unique outcomes. So the question might arise here, what are you going to do if you've got the same student? Let's say we had 44, we had 90, and then let me think this through. You had 94 instead of 54 next. That would be the same student as student 90. You're welcome to, in your random number table, if you've got that printed, just scroll this out, right through it if you want, to denote to yourself that you use the next 2-digit sequence, the 17. But again, that doesn't matter in this case. So 44, 90, 54, yet another no, and then I saw 65, 45, and 91, another no. So in this case, clearly we would estimate from the simulation that the likelihood of 3 randomly chosen girls to be in this not student-teacher, but parent-teacher conference would be 0%. Okay? One of the things to remember when you're running these simulations is that the simulations do not necessarily match up with what will happen in reality. Again, because you're using random events. Random events have random outcomes. Therefore, the outcomes that you may see would not necessarily follow reality. No different than we worked with data in a scatter plot. Okay? You may have a really good tool, and we do have a really good tool in this case with the table representing your simulation. But just like with extrapolation, it doesn't guarantee that A really good tool like a linear model is going to do anything for you in the future. We can't know that we would have we can't know that there's a 0% likelihood of selecting 3 students just based upon the simulation. Again, it's a best guess, and it's sort of a good introduction to probability as well. All right, that's what I've got for you. Your notes, I really should have announced this earlier, are also in the random number table event page.